to prevent your airfield lights, are they in danger of becoming FOD? As we know, this does happen. And so we're going to kick off very rapidly because there's a lot to go through today. Can you see my headline screen there, guys?
Yes.
Yes.
Yep.
Right.
Yes.
So today we have an eminent team of experts for you. We've got today's presenters are Seb Wolf, who is an electronics engineer specialized in airfield lighting. I first came to know him from Ernie Lucibit and then ADB Safegate. Also worked with Honeywell, consultant to Zurich Airport, very well known in continental Europe and very knowledgeable on this specific topic. And then from the United States of America, we have Mary Baton, who is the queen of bolts, as those of you know who know Mary, and also co-presenting with her Kevin Halpin from Elite Electronic Engineering, the one of 2 test houses approved for FAA equipment in North America. And then for the panel, we have Tony Smith, Keith Costel, Carl Johnson, Kev Burbage, Stuart Ford, and myself. So there's a lot to go through today. So I will start off very quickly now. Introduce Keith. Please, could you take it away for us?
Okay, good afternoon, good evening, good morning, wherever you are in the world. A quick overview before we start. In AGL, we know that is a combination of, we need to get photometric output, and to do that, we need electrical power integrity, control monitoring, civil, mechanical security, etc. And on the runway, taxiway, and apron areas, and particularly on the runway and the high-speed exits of taxiways. And today we're going to concentrate on mechanical security. And we know that when we install our light fixtures into the pavement, our in-pavement lights, then there are 2 schools of thought and 2 schools of usage in the world. There is the shallow base concept, and there is the deep base. And we're covering both of those today. Next slide. Robert, next slide, please. So we need to have the appreciation right at the beginning that, yes, we secure our light fixtures with using screws or bolts, as some people call them, or a stud and a nut. We're concentrating on the bolts today, and we tend to torque our bolts to a particular secure level according to the manufacturer's recommendations. However, torque is not the only. Torque is actually the twisting moment. The real function of keeping our lights tight in that base unit is the clamping force, and that's what we're going to cover. So I'm going to introduce Sebastian Wolf, who's going to give the first presentation, and then Mary Baton and Kevin Halpin will do a second presentation. Seb going to concentrate and introduce on the shallow base concept, where Mary and Kevin will concentrate on the deep base concept and the tests that have been carried out in the USA. Next slide, please. And let me introduce Seb. Sebastian, join us.
Hey, thank you very much, Keith and Robert, for the introduction and the opportunity to bring this important topic out into the field. Are your airfield lights at risk becoming FOD? So why is this important? FOD incidents due to loose lights regularly happens around the world, even though nobody wants to talk about it. Nevertheless, in case of incidents, especially with damaged airplanes or even worse, insurances will ask a lot of questions, finding out the root cause to address responsibilities. Standards and regulations will be created and further on adjusted to improve with rising knowledge and technologies. And that's the content of my presentations. I will start with some examples from the field for people who are already aware and long time in the industry, no new news, but for new joiners in the industry, they will see a lot of things that can happen and which things that will happen sooner or later in their future career. Correct. So starting, what can happen in the field? We can have missing lock washers. So the picture on the left-hand side. Below, we can have loose bolts. One thing also occurred in my career is we have different kind of screws. And of course, screws which are out and on the runway, taxiways, which occurred then where we can see they are deformed or broken even. Next picture, please. So what also can happen, the safety washers or the lock wedge washers, however we want to talk about it, name it, they can be assembled in a wrong way. In this situation, they are assembled on the left side with 3 washers and on the right side with only 1 washer. Either way, the function won't work. And then here we have a picture of reverse assembly of the washers. So they are not clicking into the right side into each other. Therefore, the function also won't work. They are, in that case, useless. Next, if the screw connection fails, and a screw connection can fail even with having the torque available, and no clamp force there in, the light can start vibrating, and after a couple of hours, months, maybe even years, the light can break. And finally, that's what I want to say. Everything that can happen will also happen in the field sooner or later. It's just a question of time. And finally, that's the next escalation. And inside light can be pulled into the wing of an airplane. So that's there are a couple of incidents known, but of course, yeah, as less as being talked about as possible. Yeah, so it's nothing that an airline or at an airport really want to see and talk about. Yeah. So here a few examples, and finally, what those examples will cause is investigation, an incident investigation, and also in this case, it caused a kind of new standard. And in my view, the best standard in the industry, which is the engineering brief 83, already engineering brief 83A. So what is this engineer brief about? I will come to it briefly on the next pages. So first of all, important to know, it clarifies who is in charge of this situation. It's not the OEM, whether we like it or not. It's the airport management or its agents. So the engineering brief really clarifies the responsibility of this topic is with the airport. And the important point is they introduce a clamp force value, which is something different, as already explained by Keith initially, than the clamp force and then the torque that we already know, and install our lights, inside lights with. And the engineering brief also said it's important that torque values should be determined by the testing the airport mock-up. What is that? That's a mock-up created where we identify which values are the right values in relation to few unknowns to require with input torque the right clamp force. So next, please. And one of the mysterious black hole in the inside light and in the inside light world is the K factor. So the K factor, that's something which is dimensionless, and it's a friction characteristic which will also change over time. So each time something changes then in the installation, this friction characteristics should be analyzed again. And again, who is responsible? It's the airport's management who is responsible. So next. So if you look at how we calculate this force, there are few dependencies. So the left picture is the torque. So torque is the twisting force which is applied to achieve the axial clamp force. And the axial clamp force is calculated by a very simple calculation shown here, T, which is torque. Then K is the friction coefficient. So torque, usually it comes with 25, 30, 35, 40 Newton meter. I've seen a lot of different torque settings at different airports all over the world, but it's a range of 25 to 40 Newton meter. Friction coefficient, I haven't really discovered a lot about that instead of one study that I did, which I come through later. We have a nominal bolt diameter, which is a fixed value for the M10. It's easy. And we have the axial clamp force, which then is the final target, what we want to achieve with this torque input. Yeah. So just as a quick calculation, we can say there are I can take two values at the 40 Newton meter torque level. So if you look at a stainless steel connection, a dry connection will end up having a friction value of 0.3, quite high, and therefore you will achieve approximately 1.3 kilonewton axial clamp force with the input of 40 Newton meter. If you have a bolt system which is lubricated, either dry or wet, then this friction value will come down to approximately 0.1, which then increase at the same level of torque the final outcome of force up to 4 kilonewton. So that's how sensitive this is due to the K value at the same torque levels. Okay, next, that's next page, that's the engineering brief. The first version of it calculates, finally, I don't want to go into details of the figures, but it calculates approximately 40,000 pounds and 30, which is 65 kilonewton axial clamp force. The latest version of the engineering brief even doubles that. So the requirement for 12-inch light in Newton meter is above 100. So if you go back to the first slide that I did the rough calculation with values of 0.1 and 0.3 as friction coefficients, we end up achieving on the lab circumstances a value of maximum 4 kilonewton per screw, or if it's dry, just 1.334 kilonewton. Okay, so next. So this was then due to I did a lot of studies on these topics, and I also was then working as a consultant where in Airfield really wanted to find out a new solution or a better solution, how they do it today. And initially the test was set up like a trial and error test. So we take different kind of solutions and we see how it will work in the field. After getting to know what are the important values and important criteria in this setup, I decided and recommended that we won't do this test any further, but what test would be nice and interesting to know is finding out the K value. And I went then into the field with a system which allowed a direct clamp force measurement, in parallel also seeing the torque. And therefore with this information, I was capable, first time in the industry, to capture what's the real field situation, not something in the lab, not something in the books or whatever, really what's in the field. And I think that's the most important thing, looking at this area. Okay, and the next slide, those are the results in the field. So we can see here it starts with the lowest friction value of 0.159 up to a maximum of 0.419, which then translated at the same torque setting into a clamp force, which is 11.7 kilonewton, which is too low to achieve the functioning of the safety washers, which is 13 kilonewton, so therefore not good, it's too low. And on the other hand side, it's 28 kilonewton, which is too high for the screw itself. So at that airport, they used the OEM supplied screws A270, and that's a maximum recommended clamp force of 17 kilonewton. So imagining 28 kilonewton would then deform and break the screw itself. So we have a very tight situation with the materials supplied here. Okay, that's a introduction to the product that I use. So this is this Magenta Lock product, which has a capability of measuring the direct clamp force. It comes with a data matrix code where one figure is in the screw or for the screw itself saved, which is the 0 runtime. I come to that later on. And this sensor is a chemical non-losable assembled sensor. So those are the two main benefits of this screw. So there's a information, so it's really a unique product, each and every screw itself. And the information is put into this data matrix code for each and every screw. And it's a chemical non-losable assembled sensor. It allows a direct measurement of the clamp force, which is important to really get to the point of what's this K value in the field. Those are the technology, that's the technology behind. So this product comes with a force washer combination, as well as this mechanical sensor, this chemical sensor, non-losable, and it works with ultrasonic measurement. So basically the data matrix code of each and every screw gets the information relaxed, lying on the shop floor, more or less, of the manufacturer, where the signal gets calibrated. So that's the 0 runtime. And when we then go later on to the field, it's like a spring. Actually, the screw or the screw connection works like a spring, and then it gets enlarged, and therefore the ultrasonic signal takes longer than initially tested and put into the data matrix code. And that's then the runtime difference, which gets calculated, which then comes out with the axial clamp force as information parallel to the torque that we also need to calculate the K values. Okay. So this is how the system gives a direct feedback in the field. So we will, as said, see two values. One is the torque and the other one is the force, which is through direct independence due to this K value. Good. Yeah. So that's from my side what I can bring on this webinar. And I want to conclude here with asking everybody involved already in airfield lighting to do his own risk analysis based on this, probably for most of us, new way of looking at the installations. Yeah. Thank you very much. Thanks.
Thank you very much, Seb. I'm now going to move on and introduce Mary and Kevin into the a little bit more deeper information associated, but concentrating really on deep bases. So over to you, Mary.
Hey, Mary, you're still on mute.
You guys can't hear me. Now can you hear me?
Yes, we can. Thank
All
you.
right, so I'm going to talk about the bases and the fixtures and how we're going to keep them together. Next. Just a little bit of history on fasteners. Archytas of Tarentum actually used the screw form back in the 400 BCs to get olive oil and pressed grapes. And I only bring this up because that would be like 2,500 years of talking about bolts and screw forms, and we're still talking about it. So Archimedes was credited with the water screw, and then a gentleman named Jacques Poisson created the bolt and screw in the 1500s. Then we attached a screw drive to a lathe, and voila, we made screws from a clockmaker in the 1700s, and nuts and bolts came after that. So we've been talking about it a long time. Before we talk about bolts, we always talk about bolt, but the bolted joint design is actually what's important here to start out with. The bolted joint design, the bolts can either be, the bolted joint can be in a tension joint where the forces are parallel to the axis of the bolt, or in a shear joint where the forces are perpendicular to the axis of the bolt. Next. Airfield lighting is a single shear bolted joint. It's been defined as a single shear bolted joint. Unfortunately, we can have multiple single shear planes if we have spacer rings in there. And we could have, we have threads in each of the shear planes that will weaken the bolted joint. So we have to design for that as well. Being a shear joint, it can become a bearing joint or a slip friction joint. And in a bearing joint, what happens is the members are allowed to slide or slip until they come in contact with the bearing surface, which in our case is the bolt. And that prevents further slip. Or it can be a frictional joint, a slip friction joint, in which case we need to create enough frictional force between the vane surfaces of the joint members so that the friction overcomes the shear forces that the bolted joint is exposed to. Next. So again, this is the Airfield lighting slip friction bolted joint. The forces, the horizontal forces are the plane landing, which can land, break, turn, all of that on top of a light fixture. That's the worst case scenario. And on the left-hand side, we show the forces keeping it together. Each of those red lines that you see in that deep base can represents a vane surface. And that's where we need to create all the friction. That has several spacer rings in it. By doing that, we have the force of the plane landing on it, running over the base can, plus any additional clamp load we might need from the tension in the bolts. So we have to create enough force to keep that together by friction to overcome the plane landing on it and breaking. Next. So if the forces keeping it together are greater than the forces pulling it apart, the bolted joint doesn't even see any of the forces that are acting against it. Next. But when the forces are pulling it apart are greater than the forces holding it together, the bolt will fail, and that could just be slipping in the bolted joint. These are the components that are in the whole entire bolted joint. We have the fixture, we have the pavement ring, we have the spacer rings if necessary in there, we have the top flange with the threaded holes, then we have the bolts and the washers. All the vane surfaces are major contributors to creating the friction. The more friction we have in the vane surfaces, the less we have to rely on the bolts. Next. Slip coefficients. Go ahead. This is a demonstration of the slip coefficients. So we're going to have here on the left-hand side is galvanized to galvanized. And you'll see that piece slide. All right. On the right, we have two different surfaces that are mating up on the vane surfaces. And you can see the greater the angle in here, the more friction we have between the vane surfaces. So again, next. Whoop, next. The more friction we get from the coating on the vane surfaces, the less we have to rely on the bolts. Next. Here's a little chart showing the 5 different friction coefficients of the fane surfaces now. The 0.37 in the middle is what is in engineering brief 83, 83A. As you can see that the grade 5 bolts pass, but the F593C bolts don't at the 0.37 coefficient of friction. Going to the left, if we have less friction, all bolts fail. Going to the right, we have more friction, all bolts pass. Next. Again, as Seb said, the bolt acts as a spring. As the bolt is turned, the bolt stretches, elongates, and it compresses the items in the bolted joint. The bolt wants to return to its normal length, but if you stretch it too far, it won't return to its normal length. And if you continue to stretch it, it will break. This is the classic tensile stress strain diagram. What this is showing in the bolts, we want to stretch that bolt to create the tension and the strain in the bolt. We want to keep that within what we call the elastic range. There's a place on this graph where it shows the yield point. We don't want to exceed the yield point of that particular bolt with that particular size, with that particular material. All bolts have a yield point. We must keep it below the yield point. You cannot look at a bolt and know if it's been yielded or not. Once it's yielded, it enters what we call the plastic range, and that bolt will no longer sustain any clamp load. We try to create a proof load, which is a number that's typically 85 to 95% of the yield point. We do that for some safety factor. An additional safety factor, we set the clamp load at 75% of the proof load. Again, I want to stress, you cannot, if you over tighten a bolt, it will yield, but it will look okay, but it is not going to sustain any clamp load within the bolt. Next. So we talk about clamp load, bolt clamp force, bolt preload, bolt tension, all of that means the same thing. Torque. Torque is just the means to an end. Next. Torque actually creates the tension. We do that as we turn it, it stretches the bolt and the bolt becomes longer, creating the tension in the bolt. Only a small part of that torque contributes towards the tension. Anti-seize reduces the friction in the bolt threads. This is now, here we're talking about friction within the bolt threads itself. If we put anti-seize on, we create less friction in there, so it requires less torque to achieve the proper amount of tension or clamp load in the bolt. Next. This is the formula we talked about, that Seb talked about. We're solving for torque here. So we have the torque, which is the T. We have the preload in pounds, which is the tension in the bolt. We have the diameter of the bolt, which we know. And we have the ephemeral coefficient of friction, which is an unknown. The coefficient of friction in here is not just the coefficient of friction. It tries to take into account dirty threads, damaged threads, dirt in the holes, dirt in the threads, the female threads, almost anything that they can think of that would cause to have more friction installing this, so we have less preload or less tension in the bolt. So that's how we use the formula. Next. So I want to stress again, torque is not a constant. What I mean by that is you cannot take the torque for a 3/8 stainless steel bolt and apply that same number to the 1/2 inch grade 5 bolt. They are different. They're not constant. All right. The same thing, the torque varies with the K factor. If we would try to use the same torque with a K factor of 0.1 as we do with 0.2, we would have different tensions in the bolt. So we use the formula to solve for T, for torque. The force does not change, the clamp load does not change within that particular bolt set. So if we have a 3/8 inch F593C bolt, we know what the force is at that bolt. So the torque and the K are variables. The force and the diameter do not change. As the K value goes up, the torque goes up, to achieve the same clamp load. Likewise, if the K value goes down, the torque needs to go down to limit that same clamp load in that bolt. Next. However, now torque does need to be consistent. Once we've determined what the torque value is to achieve the clamp load within that particular bolt, we should always be able to create the same force in it. So once it's determined, the bolted joint should be consistent. So all bolts develop the same tension if we turn it to the same torque value. Next. So here's the formula. We know we were solving for torque. 3,800 pounds is the rated clamp load of an F593C stainless steel bolt. That's a 304 stainless steel bolt. The diameter is 0.375 and times 0.2, which is our standard K value for dry, non-lubricated bolts. And we run that formula, and next, we find that it's 285 inch-pounds or 24 foot-pounds of torque. We turn that bolt in, that required 24 foot-pounds, we will end up with the 3,800 pounds of clamp load or tension in the bolt. Next. Now we're going to look at the torque tension Skidmore-Wilhelm. This shows the relationship between torque and tension, and it takes into account the washer friction. However, it's using new pieces, so it's not real world. Next. This is a sample of a desktop Skidmore-Wilhelm. You can see the gauge on the top, the round gauge. That's going to be the tension in the bolt. Then we have a setup in here, which is the mock-up, okay? And there's a load cell in between, behind the bolt there. So what we have here is a wedge lock bolt, which is an F593C bolt. That requires 3,800 pounds of tension in the bolt. We have the bolt there. We show you that. Underneath the bolt is the washer. So we have the washer set up in there. Underneath that is a piece of the fixture, an actual fixture, light fixture. And on the back side, we've cut apart a top flange with the actual threaded threads in it that represent that, well, it is the top flange. So this is a mock-up. The only thing it doesn't have is any spacer rings in it. This is what we call it when the EB83A talks about having a mock-up made. This is what you would do. Go ahead, next. Okay, Keith, you can run that. Whoop, back up. Back up, there we go. So this is the Skidmore torque tension test. Again, this is just for the F593C bolt, wedge lock bolt. You cannot use this with any other. So there's our gauge. We need to turn to torque this bolt until we get up to 3,800 pounds, which is the clamp load for a F593C 3/8 inch -16 bolt. And then on the right-hand side, you can see the torque requirement. So we're getting close to 3,800 pounds. And there we are. And there it is, 43 foot-pounds. Next. So you can see there's a vast difference between using the formula, which told us we only needed 24 foot-pounds to get to 3,800 pounds of clamp load, and 43 foot-pounds. Most of that is due to the washer difference, because we use some aggressive washers in there. That takes up a lot of, that creates a lot of friction. So that's why we need the additional torque. Torque is our most cost-effective guess at tension up to this point. This is an estimate from the Industrial Fastener Institute. NASA's done some other ones, which says that strain gauges will actually, if you could put a strain gauge in there and measure it, you're plus or minus 1% of actual, the relationship between the tension in the bolt and the torque. All right. I mean, and the torque wrench is about plus or minus 25%. Operator feel plus or minus 35%. Seb talked about the ultrasonic magenta lock bolt. That has been, it falls within the range of the strain gauge, so it's very accurate. Next. Kevin.
All right, thank you, Mary. So now that we're all up to date on our bolt knowledge and torque and tension relationships and how bolted joints work. I'm going to go through some of the, in the United States, the FAA requirements for the other equipment that's in the bolted joint. So the base cans and the light fixtures and spacer rings. It's important to note that the FAA does not have any qualification or certification requirements for bolts themselves or for washers. So I'm going to go through the base cans and the light fixture requirements related to the bolted joint. For base cans, that's divided in 42J. Specifically, the L868 type load-bearing base can is used for centerline lights and threshold lighting, where it could be there could be aircraft or heavy vehicle loadings on a regular basis. And so the design and dimensions of the flange, which is the interface for the bolted connection, is common for all manufacturers. It's a required design and layout and dimensions. Now, different manufacturers can use different materials to make it. Typically, they're made of A36 mild steel that is then galvanized, or you can also typically get a 304 stainless steel base can. So those are the different materials created. You're allowed to use, at the airport, you're allowed to use up to 3 spacer rings as long as the total height is less than 2 3/16 inches. So that creates some additional fang surfaces and movement and longer bolts within the joint. Now, there's a lot of qualification tests for base cans. I kind of pulled out a couple that are related to how the actual bolted joint works. So the first one would be the load test that's performed on the base cans, which is a 450 PSI applied to the top flange to check for deformation or movement of the flange under that loading. So that would kind of simulate an aircraft rolling over or sitting on top of a base can. And then the other one is the flange bolt torque test, which uses 18/8 stainless steel bolts, and you insert them into the tapped holes in the flange and turn them until the stainless steel bolts fail. And the point there is to check for any damage or deformation in the threads that are formed inside the top flange. Next. Then the other major component is the light fixture itself. So on the right, I have a kind of a exploded view of a typical in-pavement light fixture. You see the top cover, which is the part that's exposed, and that's the part that gets bolted onto the base can. The rest of the components just attach to that cover underneath and sit inside the base can with the isolation transformer and any other equipment that's needed in there. So 46E defines these requirements for runway and taxiway in-pavement light fixtures, specifically the L850 and L852 types. Again, designed to withstand aircraft and vehicle loadings. Come in 3 different sizes that are defined. The top housings can be made of any material, but they're typically made from a cast aluminum. And then there's a whole long list of test requirements for this equipment, but again, the ones related to the bolting joint and the fixturing onto the base can are a load test, which is the same load test that's conducted on the base cans themselves, the 450 PSI, uniformly across the cover. There's a vibration test. It goes up to 15 Gs for 10 minutes in all 3 axes of the light. So it's a pretty severe test. There's a horizontal shear test. So this is the only thing that kind of approximates an aircraft or a vehicle rolling over or skidding over a light fixture and imposing that shear force on the bolted joint. But the load is only 3,000 pounds. It's applied 20 times and there's no load rate required. So it's usually done pretty slowly. So again, I just want to reiterate, yeah, there's no at an equipment level, there's no qualification or certification requirements for bolts, washers, or the bolted joint itself. It's just kind of an end result of the different parts and equipment that go together. Next. So for airport operators and maintainers, it's important to think about when choosing bolts and how your bolted joints are going to work, what environment they're operating in. So what do the equipment and the joints have to withstand? From a temperature perspective, we always evaluate equipment between -40°C to +55°C in operation. You've got to consider the corrosion environment. It could be water, salt spray, de-icing fluids, even things like oil and fuel, all things that end up on the pavement and eventually get into the light fixtures. Then you have other environmental exposure for things like sunlight, rain, snow, ice, standing water that all have to be accounted for, which all of those things also contribute to corrosion as well. vibration from aircraft and vehicle movement, the types of vehicles that are going to be on your airfield, from just passenger cars to heavyweight tugs, construction vehicles, and snow plows are another major issue for the northern climates. And then what we're most concerned about is aircraft operation, which is landing, braking, taxiing, turning, high-speed rejected takeoffs, things like that are all exposing those lights to extreme forces. Next. So at the FAA Engineering Brief 83A, which we talked about earlier, kind of defines, has some best practices for bolted joints and defines the worst case condition to be evaluated. And it assumes to be a heavyweight, a large aircraft, maximum braking at high speed at its maximum takeoff weight. So really it's a rejected takeoff scenario where an aircraft is accelerating up near its V1 speed, where it's going to be committed to take off, and then the takeoff is rejected, causing a high speed, maximum braking, full weight event. We assume anti-skid systems are working. And pretty much every modern aircraft has an anti-skid system that prevents the wheels from locking while it's braking. So you've got a rolling wheel going over the light in that scenario. And EB83 also analyzes the joint as a slip critical friction joint, meaning that any movement of any of the pieces within the joint when under shear loading is considered a failure of the joint. Now, does that mean the lights will actually, the bolts will fracture and the light will dislodge from the base can? No, not necessarily. It just means that there's going to be movement, and over time that movement can lead to other types of failures. EB83 assumes clamping force as the critical parameter in your bolted joint and a friction coefficient of 0.37, but that friction coefficient will vary depending on what materials you're using, what first surface coatings you have, how many spacers or extensions, the length of your bolts. So that is definitely not a fixed value. So our question then is, does that analysis within EB83, which is being used to determine what clamp load and what bolts are needed in your joint, does it actually reflect what happens in the real world under that loading condition? Go ahead and go to the next one. So what we did is we developed what we call an instant shear test method, since we felt that the horizontal shear method in 46E was not sufficient for this high speed, high force scenario. So on the left, you have what happens in the real world. You've got a braking aircraft rolling over a light, imparting a shear force through friction with the tire, which then it happens very quickly, over about a 4 millisecond time period. So in our lab method, instead of using friction to move the light, we use a hammer on the side, which then imparts a force to the side of the light fixture and then creating that shear force between all the different shear planes. And we can control the impact force and the time duration. We're achieving, basically about 1 millisecond impact duration with our current setup, but we can vary that. And so what this does is it eliminates all of those variables that go into the EB83 analysis and calculation by just, using a physical test to simulate the forces involved in that high-speed braking event. And we sized it down for just one single bolt rather than a 6-bolt installation, but the assumptions in EB83 are that there's even clamping force with all 6 bolts in the fixture. So we just did a simulation with 1 bolt on all the same components. So now Mary can talk about some of the results of operating this test and the horizontal shear test that she's conducted.
Okay, so this is the setup for the normal, the one that was found at -46, the horizontal shear test. You could see that you set up the fixture, you weld a bar on, and you push down on that bar, and you do it very slowly. You're only going to 3,000 pounds. So you do 20 cycles in each direction. It goes from 0 to 3,000 and back down to 0, and so on and so forth 20 times. Then you take it apart, you put it back together, and you do it 20 times the other direction. This is not reflective of actually what's happening out on the airfield. That's why we went to the instant shear test. Next. So in the instant shear, it simulates the aircraft landing, braking, fully loaded. It's instant. The impact duration is very short. It's much more accurate simulation of the forces on the runway and the in-pavement lights. Next. This is an example of a grade 5 bolt with galvanized fane surfaces. We drop the hammer on that, ends up with 0.55 milliseconds with significant bending is the end result. Next. This is the same test with a F593C stainless steel bolt. So we can run this test in multiple configurations. Significant bending. Go ahead, next. The instant shear test, those tests show that we have similar results for both the F593C and the grade 5 bolt. Next. So when we dropped it down to 1,700 pounds, which is what is found in the EB83A, again, both bolts performed adequately or similarly. There's little to no bending in either bolt. Next. However, using the carbon steel bolts, we ran into another problem with corrosion. Once the coating is knocked off a carbon steel bolt, it begins to rust. There is no coating manufacturer that guarantees that that coating will stay on due to mechanical damage. There's just no one. So we decided we'd do another test, which is we would do the instant shear test we just showed you, and then we would run these bolts through the salt fog test, and then we would do a tensile testing to see what happened with if we have any loss of material, any loss of strength. Next. So here's the instant shear impact test. Next. And this is this is our salt fog test. So as you can see, we did 4 different groups. The bottom one is all grade 5 coated bolts coming after going through salt fog test. Group D is F593C coated bolts, coasterized bolts in the center, which did not perform well without some kind of a coating. And we had a Bumax 88 bolt, which is a coated stainless steel bolt. It's a 316 stainless steel. Next. Then we did the tension test. Next. And this is the results of the tensile test. This is kind of concerning because the grade 5 bolt, you can see on the gray dotted line, actually lost 7.5% of its strength, and that was after 1 cycle, 3 strikes. So this is something that needs to be looked into. We don't know if that's just a one-off or if it hits the 7.5% and that's it, or does it lose 7.5% each time, or how long does it last before we have no strength left in that bolt? That's something that needs to be looked at. Next. And I believe, Kevin, you're up again.
Yeah. So I'm getting back to the EB83 clamp load calculations that are defined in there. So after, Mary's test results, they're kind of showing the impact of corrosion on different types of carbon steel versus stainless steel coatings and the impacts and tensile strength. Those should all be things that are considered by an airport or a maintainer to determine what is best for their bolted joints. And obviously a desert airport is going to have different requirements than a coastal airport, based on that difference in environment. So what EB83A does is it defines that 4,900 pound clamp load as being sufficient for a modern governing aircraft. But individual airports can evaluate based on their traffic and their environment and still be compliant with EB83A. So my first point there is to say that compliance with EB83A is only required for AIP funded projects. And now it's a best practice to make sure you have a solid bolted joint and that you're maintaining it properly. But actual compliance is only required for AIP funded projects. So now the 4,900 pound clamp load that's recommended in the EB83 again is considered for an A380-800 aircraft as the modern governing aircraft. So essentially the highest loaded, most severe scenario. Now in the US, there's only about a dozen airports where A380s actually operate. And there's not even that many of those aircraft in operation around the world. So it's kind of a limiting scenario. So what individual airports can do is determine what is the governing aircraft for your airport, which is the heaviest wheel load that has at least 250 annual departures. Now, not 250 operations, but 250 departures, since that is the worst case scenario of a rejected takeoff at heavy weight. Appendix B includes all the sample calculations and the variables that need to go into that. Some of them can be difficult to find, but luckily aircraft manufacturers publish load planning manuals for all of their aircraft that are certified, so that you can get the loading information you need to fill in all the variables in that calculation. And I've got some links to the ones from Boeing, Airbus, Bombardier, but Embraer and other manufacturers also publish this information publicly. If you can't find it on their website, if you contact them, they'll provide it to you, because it's a requirement under, at least in the United States, the FAA requires aircraft manufacturers to publish this information. Next. So here's some examples of different aircraft going through the EB83 clamp load calculation. And what you find is that actually the A380 is not the worst case scenario. An A340-600 requires an even higher clamping load, as well as an A330, even an A321neo, and a 737-900, or no, a 737 MAX-10, which I don't know if those are in operation yet. I think that might still be going through certification, but the information is published for it. And those actually exceed grade 5 proof load, clamping load scenarios. So if you have those aircraft, even a grade 5 bolt is not EB83A compliant. And one way to simplify these calculations, you'll see down at the bottom that for most of these larger aircraft, the tire footprint, the contact area, is larger than the light area. This whole calculation simplifies down to a function of tire pressure. So that can be your very simple, easy guess at what clamp force could be, give you at least a close number. So this is all information that airports individually can find and use based on their operation and still be EB83 compliant, and not necessarily have to use grade 5 bolts or follow the final recommendations for the A380 that are in EB83A. All right, next. I think that's it. Yeah.
Thank you very much, Mary and Kevin. I think that's been quite an enlightening presentation, both from Sebastian and from Mary and Kevin. And the key issues is that safety is non-negotiable. And when we're looking at safety, we look at the elements associated with our lighting fixtures, whether it's a 12-inch fitting or whether it's an 8-inch fitting, whether it goes into a deep base or whether it goes into a shallow base, there are those variables. But of course, what brings the base unit and the light fixture together is, of course, that securing mechanism. The securing mechanism is going to be either a stud or a nut, which is used quite a lot around in the shallow base theatre, or the screws, the bolts, whatever you want to call them. And,
Keith, can I just interrupt
yes.
you? Could you, much as that's an excellent slide you've got up there, could you turn your camera on so we can see you?
I can't because it's. I'm trying to get I've got a virtual thing up and I can't get it off at the moment. I've been trying. Okay, so I'm sorry about that.
Some might say it's an improvement, but anyway.
Yeah. So, but yeah, when we're looking at security and we're looking at the compliance of our lighting fixtures, we are, ultimately compliance is, does it get the photometric output? But what affects it, of course, as I said right at the beginning, there are the mechanical loads, there's the electrical factors, and there's the civil. The civil and the mechanical go together, and we've now had a very, very good introduction to the mechanical side. What would be very interesting and is really a call to the industry, whereby perhaps a collaborative approach to have a look at it collectively internationally. And it's the Americans that, in the US and the FAA with the Engineering Bulletin 83 series that have led the way in this. And really in the rest of the world, it's been left to the manufacturers to make the recommendations of how we should secure their light fixtures into their bases with their torque levels. But it's a very, very important subject, and especially when we're looking at landing and the high-speed exits, rapid exits, and of course, as Kevin has explained, is when there is an aborted takeoff and the braking elements. So really, really important subject. Now, technology is moving forward, and we are in the world of algorithms and AI, etc. So, you know, I would say for us is now looking forward is this call to the industry for a collaboration to bring it together further.
Yes, thank you, Keith. Yes, you're quite right. I see that, you know, as I think it was mentioned in the presentations earlier, the FAA, you know, with EB83A has the most comprehensive description of what needs to be done. But we won't go into the detail here, but there are flaws in the calculations there. Those are being addressed directly with the FAA by this group. The ICAO doesn't specifically mention anything, but it does say a maintenance program, including preventative maintenance where appropriate, shall assist a maintenance program and a system of preventive maintenance where appropriate should be established at an aerodrome to maintain facilities in a condition that does not impair the safety, regularity, or efficiency of air navigation. And I guess it falls within there. But there's certainly more work to be done in this area because, as Sebastian pointed out in his presentation, this is kind of the secret problem we have here. It happens more frequently than anybody likes to admit, because it's embarrassing, it's not talked about. But it comes down to something which you may have heard me mention in the past. You can't manage what you don't measure. And so the work, obviously, we need as an industry to optimize the fasteners and the processes we adopt to ensure the minimum amount of maintenance interventions. But then we need to monitor and manage that by measurement. And when I talk about that specifically, we need to check at appropriate intervals, and the appropriate intervals are determined by the effectiveness of the fasteners as measured by the angle moved of the bolt or the nut and the brake torque of the bolt and the nut. So to catch them before they become loose.
One of the things, Robert, which has come up in one of the questions, and it's a very, very valid question, is of course there are going to be times when the bolt will become damaged and or the thread becomes damaged in the base. Now, what happens when the thread becomes damaged in the base? One of the engineering solutions to rectify a thread is to use a helicoil concept. Now, that changes everything, of course, when we're looking at calculations.
Absolutely, and so that's where the usefulness of actually measurements and managing and measuring comes into full play. So let's go around the panel now and ask them for their experiences in this region and what they think should be done to enhance the effectiveness of the fasteners to avoid airfield lights becoming FOD. If I start off with Carl, for example. Carl, what are your thoughts on this topic? What's your experience?
My thoughts are is being trained to deal with electrons and not bolts. I'm very curious as to why. I'm going to address the elephant in the room here in the States. All the materials are standardized. Why can't there be one torque value for the bolts? Instead of airport A torquing to 35 foot-pounds, airport B torquing to 37 foot-pounds, airport C is torquing to 20. Give me something with a standard setup, or if the NEC's compound is there, what can be done with that? To me, there should be some standardized way of doing this, not opened it to 47 different routes to get from A to B. And then the third thing I've got is when it comes to rechecking the bolts, I can understand checking them the first time, the second time, or the third time to get a pattern on where they're coming loose at. But the majority of them, in my experience, are like the lug nuts on your car. You tighten them once, they're good. If it's in the touchdown zone on the runways, you may have some that loosen and turn, and in the high-speed exits, they may loosen. But pretty much on the straightaways and taxiways, I don't understand the need. And based on the torquing checks that are being done by the airports here, there doesn't appear to be the need to check the torque on a taxiway centerline bolt every 2 months. And so I will leave it with that.
So, Sebastian and Mary, possibly you could just reflect on the question: why can't we just have a standard 35, 22, 40? Why do we need different numbers? If we define using common materials.
So maybe if I can start, in my view, the technology moved on from big cans where the calculations once were done with a lot of space, with a lot of safety factors. I'm also connected with R&D of car manufacturers in Germany. They, for example, add a safety factor of their torque of factor 50 compared to initial engineering brief of factor 2. Why did they do it? I can only assume because they understood that there is too less space to put one standard above all covering it. Yeah, because only 2 screws in an 8-inch light can't cover the requirement. Now we are at the requirement of 100 kilonewton, and with 2 bolts, it's impossible. Finally, yeah? It's really impossible. So the mechanical knowledge, due to the knowledge of R&D focused LED and electronics, the mechanical focus disappeared away, and we left that behind. And now we are somehow stuck in a situation where we have to find the next best alternative. I think we can't fix everything, but we have to find the next best alternative. Yeah.
Yeah. So I think I mean clearly you could introduce, if you could commercially introduce standardization into the cans, the bolts, the washers, that would certainly assist in the holy grail of achieving a standard value for torque. However, you then have environmental conditions and the various lubrication factors and the aging of the materials, which would also introduce some variable. But it could be narrowed down, but it would require a significant investment in research and development and analysis. So the next one, I see that we have some
I'd like to hear Mary's comment on that.
Oh,
I'd like to hear Mary's comment on the question.
The question of standardizing, Carl's question on standardizing one specific torque. I believe that they did try to do that within Engineering Brief 83A, where they established the minimum clamp load of 4,900 pounds, which reflects directly back to the grade 5 bolt. But it's also dependent upon what the anti-seize is, and that changes all the time. And so the FAA does not want to specify and say, you must use Loctite red 26, and that's all you can use, because that would give you a more consistent torque, but it doesn't give you, if somebody wants to use Loctite blue 29, then they'd have to do something different. So they don't specify and don't want to specify that you have to use a certain product on the one hand, but they do specify it on the other hand. So I don't know, it's not quite the lug nut situation. The lug nuts are the problem with the lug nut situation is it's over-engineered. The problem that we have with the aviation bolted joint is it's under-engineered. Everything about it is right at its very limit or less. There is no safety factor anymore. If you look at EB83A, there is 0 safety factor in any of those calculations. There's not twice times the safety factor at all. So I don't know how we're going to get around that or how we're going to address that, but we need to address it. So Carly, I mean, it seems it's like it's pretty simple to do that. It's not quite the same as electricity where you just plug it into the wall and all your things work. I don't know how to get around it is what I'm trying to say. I don't know how we can establish that with our current situation. Does that make any sense? Kind of what Sebastian.
I mean, that's yes, right now that is where we are. I
Right.
think work that can be done to mitigate the risks, but ultimately we're looking at having them all of the fastenings actually work, but some of them work less well than others. So that's where the measurement comes in. And but for the industry, we don't want to have to keep we don't want to be out there on the runway measuring. We want planes on the runway. So
Every
we
2
want
months, right?
we want the industry to come up with the optimal fastening that requires the minimal amount of testing. But until that comes along, I'm afraid we're stuck with more measurement and testing.
Yes.
So, Kevin, what are your experiences on this topic?
Well, I would say that it's important to look at the bolted joint as a whole rather than focusing just on the bolts. Bolts are one part of the joint. So there's a lot of other variables that go into it. And as Mary talked about, you change the surface friction of your components. It makes a huge difference on the clamp load requirement and your bolting requirements. So that's, and she also mentioned that the bolted joint is under-engineered, and it absolutely is. There are some design changes that could be made, both on base cans, on light fixtures, on fasteners together, to help solve that problem. To design a better joint rather than just focusing on the bolts themselves. Like coming up with stronger bolts is not necessarily the answer. More bolts, stronger bolts is not necessarily the answer. There's other things that could be done. So yeah, that's kind of my perspective, is to make sure when you're thinking about this, that it's the entire joint and not just the bolt that we got to worry about.
And so Tony, as someone that has probably played a greater part in setting the regulations than anybody else on this panel, probably on the call in or anybody in the world. How do we get to a situation where somebody, is this the regulators that should be implementing the testing, the evaluation, the research into this topic? How do we improve the situation?
In this day and age, I don't know how you achieve that, but you certainly do need to have a test program and some proper research done, coordinated. ICAO is a good place to coordinate work done in different locations around the member states, but there needs to be a coordinated program. That was always the way that the basic AGL was developed. It refined down a whole lot of options and ideas to a standard which was pretty well universal. But that can't be done unless there's money put into the R&D phase of it. That's the rub, I think. What I'm hearing, there's much more to be done. And but what I would say is that this isn't, mechanisms isn't my area of specialization, but I've really enjoyed listening to the presentations. I've learned a lot. They're really good, I think. It's left me with a thought, going back to our last webinar a month ago, where I think two things came out about the whole business of AGL maintenance. And that is that you can't take a standard electrical engineer and just rubber stamp him and say he's competent to do AGL maintenance. It is almost a job with a special requirement and needs the adequate training in across not only optical but electrical, mechanical, engineering. They need to have education in all of those to be a really competent, certainly a manager of an AGL system. And that I think is vital. And also the other thing I would say is some of these issues about what is the best, seem to me, what's the best bolt solution, what's the best design and so on. This is where the maintenance people, with their knowledge then of what helps them in getting an adequate level of maintenance, they must need to be in at the procurement phase to have a say in what is going to be built into the airport that they then have to manage, which equipments are better from a mechanical point of view. You don't get a shout usually. Usually get the thing handed over after it's been accepted by the money boys and the top management, with no input at all into whether this is really going to be easy or very difficult to maintain.
Yeah, thank you for that, Tony. I think, Kev, that raises the issue. Tony raises the issue of competency-based training and assessment. Can't be. We need to be able to demonstrate relevant training in the key areas to function, and we need to be up to date in that training. So how are modern day training methodologies addressing this need?
Essentially, we're looking at obviously following the ICAO principles, but also we're looking now at the technician and what they do on a day-to-day business in the field, because there's lots and lots of things where there's been no sort of like refresher training going forward, and we need to sort of get into the nitty-gritty of what fails and whether we can actually improve the way that that's managed. So there's lots and lots of areas on the training side of it that we can look at, and certainly with bolt failures, the number of people that over tighten bolts is incredible. They're not torquing the bolts correctly at all. So that's something else that we see, and obviously that leads to shears and then people having to grind things out and stud extractions and stuff.
Yeah, yeah, this is an absolute key issue, and I'm pleased to hear it's something that is addressed in the new standards. But then it behoves the industry to actually invest in the training of its people, but also in the industry itself. And this is coming like a boomerang back to Seward. I'll give you an early warning. This comes back to Seward, where we've been talking. My assessment of the world of aviation regulation is that that very much FAA is the leader in terms of funding active research and development, and through the various passenger fund levies and the like. The tech center in the US for the FAA is kind of the leader in this area, and the IES, the Illuminate Society of North America, Airfield Lighting Group, of which we are all members, and represents most of the nation's US nation's airports, has a committee to liaise with the FAA, and we've recently been talking on this very topic. Seward. So Seward, what are your, how do we encourage the FAA to do that? Because I think they're in the best position. How do we get this research done?
Well, a great question, and that's a question we're all looking for the answer to. But I think, first of all, we've talked about a number of issues here today, but I think we have to define the issue that we want to attack. And then we got to get the industry involved. The industry in a collaborative effort to get involved to define how we're going to solve the issue that we just defined. And then with that effect, I think we can start affecting the FAA and the ICAO people. But we need the clout to do that. And up till now, it's all been helter-skelter. We have an IES committee that meets with the government, the FAA, and they talk about things in the sky. We don't get down to practical issues. How are we going to do? We got to define the issue, and then we got to get the people interested enough to realize there is an issue. And then secondly, get together and give our position to the FAA and say, here's what we want to do. That's as simple as I can make it.
No, I think that's a good suggestion. So we're now running well over time. So I'll leave it to Keith to give us a final word on this topic. But feel free to keep in touch with us on and ask any of your questions, and we'll do our best to answer. But over to you, Keith.
Well, I would say I would really just repeat what I said earlier, and actually confirm what Sud has just said. We really need a collaborative program on various subjects, but of course this particular subject, and I think we should call for industry collaboration and then put something forward.
Yeah, good. So I think we can all see what needs to be done here, and I know that we're actually in North America. There's an initiative started by a group of us to actually pursue this process. So rest assured, there is action being taken on this very important topic. How long it will take, how effective we are, well, it needs all of you to lobby your suppliers, your local regulators, and all push for this, because we know it's an issue. We all know it's an issue. We can't hide from it anymore. It's important and it needs to be addressed. So on that note, I'd like to thank you all very much for your participation today, for joining us in today's webinar. I'd like to thank the panel, Kevin, Kev, Tony, Sebastian, Mary, Seward, Carl and Keith, Damon and Felicity for making this webinar happen. And thank you all so much. And I look forward to seeing you at the last Tuesday of April, when we're talking on the topic of, Keith?
Earth's grounding. Grounding, earthing networks.
This is in a way
counterpoise earthing networks.
Yes.
There are the differences.
Yeah, so it's in a follow-up to our presentation, to our webinar of a couple of months ago, when we were looking at insulation resistance and measuring. So we're looking at the electrical circuits and counterpoise and earths, and to try and optimize, well, to address the issues and to optimize the results for the effectiveness for our industry. So I look forward to seeing you all at the same time next month. We will send out links and opportunities to register. But thank you all very much, panel. Thank you to the audience, and thank you, Damon and Felicity. Have a nice month.
Yeah.
Thank you.
Thank you.
Bye.
Thank
Thank you. Also, from my
Bye.
side.
Thank you.
Bye-bye.
Thank you.
Thank you.